In this video, I'd like to tackle a beam problem with a distributed load. So here, I'm presenting a beam problem where the beam has a length L. I'm given in the problem statement that the Young's modulus and principal moment of inertia in this problem are both constant. And I'm asked to find the displacement at the center point or the midpoint of my beam of length L. Because I'm asked to find the displacement at the midpoint, I need to have a node at the midpoint so I can calculate the displacements at that node. Because I need a node at point number 2, and because I don't want to use a higher order method, I'm going to break my beam up into two elements. Element number 1 with node 1 and node 2, and element number 2 with node 2 and node 3. Now, I have a distributed load in this problem, but the distributed load is in fact a constant distributed load. I'm calling it a W as a function of x generically, but in this case, my function of x is not a function of x at all. It's a constant negative W. Perhaps this distributed load represents the density of my beam, and when multiplied by some length, it will be the weight of my beam. Okay? At each endpoint of my beam, I have an immovable wall, so I expect V1 and Phi1 to be 0. I also expect V3 and Phi3 to be 0 due to the immovable wall mounts. Now, as I said, this problem has a distributed load, so I can't use the equations that I used for the direct method because they can't handle a distributed load. I need to use either Glurkin's method or the principal minimum potential energy method. But I don't have to spend a lot of time choosing between which method to use because once I've derived my formula, I found that they arrived at the same linear algebra equation. This linear algebra equation here. The only reason for the principal minimum potential energy method or the Glurkin's method was to arrive at this formula. This is the formula I will use for all of my beam problems. I can even say I can use this formula for a beam problem without a distributed load. I would just say Wx is 0, so therefore this term is 0. Now, in this equation, I'm integrating from 0 to capital L. But these integrals are generic integrals. Remember, this is from 0 to L, the length of my element. This L here represents the entire length of my beam. So to clean my math up, I'm going to define a new constant, lowercase l, which I will define as 1/2 of the length of my beam. Now, in this particular problem, E and I are constant, so the E and I can move outside of this integral. I know what my matrices, my vectors, row vector B and column vector B are. I know this will result in a 4x4 matrix, which I already know the form of. I also know that this P represents my external forces. I don't know external forces at node 1, but I do know external forces at node 2. Applied at the node are 0. The distributed load will be calculated by this term here. So going forward with that for element number 1, I will get this form. This is my local stiffness matrix derived in a previous video. Notice these are now lowercase l's, the length of the element. This is also a lowercase l. I'm going from node 1 to node 2. This is my local displacement vector. These 4 terms are the 4 shape functions I derived earlier. In this particular problem, my distributed load, which would normally be inside this integral, was a constant, so I could move it outside. And remember, it was negative W, which is why I have a negative sign here now. Again, also notice that all of my shape functions are now defined in terms of lowercase l because that L that showed up in those shape functions was the length of the beam. I've also inserted my knowledge that while I don't know the force applied at node 1 and the moment applied at node 1, I do know that there's no point force or point moment applied at node 2. This is all for element number 1. I can do the same thing for element number 2. My local stiffness matrix will be the same. Again, I'm integrating. Now I'm integrating from 0 to L, not from L to 2L. That is because the way I defined my shape functions was from 0 to L, and I have to keep that methodology. In this particular case, my distributed load does not depend on X. W would be inside my integral, and I'd have to remember that I would need to shift my function w of x over by length lowercase l. So everywhere I saw a w of x, I would need to change that to w of x plus lowercase l. If I had a third element over here, it would be shifted by x plus 2l, and so forth. Again, I know my external force and moment applied at node 2 are 0, but I don't know the reaction forces at node number 3. Okay? These integrals are integrals I can solve. They're kind of hairy, but you can use your calculator to solve them. And you're only going from 0 to L, so the lower bound, all these terms will be 0. You can go ahead and do that for you, and you will get your equations in this form. Note, once you evaluate these integrals, which you will be able to do once you have your function w of x that would be given in a problem statement, you get simple numerical values for each element or each member of these vectors are essentially your local body force vectors. These vectors represent forces applied at point forces applied at nodes. These represent equivalent forces applied at the node that represent the forces and the moments due to distributed loads. Once I have my local stiffness problems written out, I can assemble a global stiffness matrix and a global problem. So here, again, I'm just re-showing the two local stiffness matrices so you can see how they form the global stiffness matrix. Again, I'm taking this matrix, I'm placing it here. I'm taking this matrix and I'm placing it here. The 4 elements here and these 4 elements here get added together. In this case, I have a 12 and I have a 12. So I get 24. I have some terms that will cancel each other out. Negative 6L, 6L will cancel out. I'll get 0 here, 0 here. I'll get 8 lowercase l squared here. I tried to line these problems up so you can see that these two rows that apply to V1 and V2 and Phi2 are the same two that apply to V2 and Phi2 here. These two force vectors need to be added to these two force vectors. I have a negative 1/2 WL here. I have a negative 1/2 WL here. Will give me a negative WL. This term and this term are equal and opposite, so I will get 0. Once I have this problem formed, I want to go ahead and solve for my displacements. Highlighting in red, I'm really just simply solving this 2x2 problem that represents these terms here. That's fairly simple to solve. I will find that V2 equals negative W lowercase l over 24 EI. I will also find that phi2 equals 0. Now, a point about phi2 equaling 0. It equals 0 because I have 0 over here, and I have a 0 in this term, and the only way I can get phi2 will be multiplied by 8L squared. The only way I can get a 0 over here is if phi2 is 0. But I should have known it was 0 from the get-go, because you may have noticed this problem is symmetric. And so I didn't need to actually assemble two elements and form a global stiffness matrix. I could have left this as one element, set as one of my boundary conditions that phi2 has to be 0 due to symmetry, and solve that way. The reason I didn't is I wanted to use this problem to demonstrate assembling a global stiffness matrix and a global force vector that included body forces. But if I had this as a homework problem or exam problem, it probably would have made more sense to use symmetry. Now that I have these displacements, this is what I was actually asked for in the problem. If I wanted to find the forces and the moments at node number 1 and node number 2, I could do that by plugging these values into my force vector, my displacement vector, multiplying my displacement vector by my global stiffness matrix, and solving for the only unknowns would be I'd have 4 equations and my unknowns F1, M1, F3, M3, which, if you wish, you can do on your own as an exercise. All right, we're going to have a week off from videos. I believe if you're taking our course, you'll have an exam next week. After the exam, we will start moving on to full two-dimensional problems with that, no longer thinking in terms of one-dimensional beams and bars, but actually solving for strain and stress inside of two-dimensional objects.